Okay, so I answered this one just really quickly, and I didn't like my answer. Now, the answers, if I share this real quick, the two, and well, A and E are the two most popular. Again, there's only what 10 people who put an answer in, so it's not like we're dealing with a giant sample size. B and C both got a little bit of love. No one thought D. That one should be immediately ruled out. Now, 50, okay, let's just try and jump to it really quickly. A can't be it. The bins have to be the same size. And so the fact that this one is, sorry, let me stop sharing. The fact that number one has a narrower bin, it only goes from 50 to 55. It has to be consistent. So we would cross this one out. D we can rule out right away. We would want to rule C out pretty quickly as well, because we have the skew from our box plot is showing it's going to skew to the left. The problem is that E looks immediately, I answered E. And I was just right, really quickly I looked at it, I was like, oh, that's left skew. Except notice that our quartile right here is really wide, which means this wide gap from 10 to 50 has as much data in it as this gap from 0 to 10. So that means B is actually our best choice. So it looks like we have a bimodal distribution, quite a bit from 50 to 60, and then the same amount from 0 to 50, but most of that concentrated at the low end. All right, so anyways, that can help you, and maybe this is a, what's the word? This is a warning or just a good case of why you shouldn't rush through things. And anyways, let's call that good. So look at what we've got going on today. Now this, you see it says two different things we're going to cover today. We're only going to do half of it. We're only going to do confidence interval for a difference of means. All right, I'm going to give you a little bit of a heads up today on, well, maybe not today. Never mind. Whatever the case, we have two different things to keep track of when it comes to means. And anyways, we're going to just focus on a confidence interval for a difference of means. Here is the situation. Mr. Wilcox's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rate. 20 students in the class volunteered to take part in the experiment. All of the students measured their initial pulse rates in beats per minute. Then Mr. Wilcox randomly assigned the students into two groups of 10. Each of the student in the first group drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. All the students then measured their pulse rates again. The table displays the change in pulse rates for the students in both groups. And there it is. There's your data. So construct and interpret a 95% confidence interval for the difference in true mean change in pulse rate for subjects like those who drink caffeine versus those who drink no caffeine. All right. So that's what we're going to do. I will say this. First of all, if we look at the diagram, it tells us right now that it's final pulse rate minus initial pulse rate. So we need to understand what the data is referring to. Positive means that this person's pulse rate went up by 8 after drinking caffeine. This person didn't have caffeine, yet it still went up by 3, and so on. If it's negative, the pulse rate actually went down. So with doing nothing, we can just look at this and figure out if we have any evidence that caffeine or no caffeine, that there's that caffeine has an effect on pulse rate. We can just do an initial estimate. And based on this, do you think we're going to find that there is a difference, a true difference in caffeine versus no caffeine?
Yeah.
So intuition is yes. And here's the thing, intuition doesn't have to be correct because we're going to get to check it. So it's just maybe something to keep in mind. Maybe so you can be surprised one way or the other at the end. Okay. So as far as this goes, we've got two samples because we have a sample of people who drank caffeine, a sample of people who didn't have caffeine. All right, enough on this. Now, actually, one thing I wanted to say is that later, it'll probably be on Wednesday and Thursday. or somewhere in that range. We're going to be looking at another situation. I want to be somewhat vague about it, but we're going to look at another situation where we might have a table like this, and we have to set up a confidence interval and hypothesis test differently than what we're going to be learning these next couple of days. And we're going to talk about why we would do it one way versus the other. But I just want to point out this kind of table can be read in different ways depending on what variables we're talking about. And I just want to make sure that's clear from the beginning. Okay, but I want to keep it somewhat vague. And sorry if that is just too confusing. So I got rid of the prompt. We still have the data, and that's what we're going to need. So the first thing we want to do is find the mean and standard deviation for each group. Now, if this is an AP question, they would give you the standard deviation most likely because you don't solve that by hand. So what you're going to do is let's just take a second there and we can figure out the mean and standard deviation for caffeine versus no caffeine. All right, so again, this is maybe just a little bit of review on how to find your data. And this may be unnecessary review because like I said at the beginning, if this is a real AP test and they wanted you to come up with a confidence interval, you wouldn't be calculating the standard deviation. That would have to be given to you. But now we can see 3.2 is the mean for caffeine and 2.70 is the standard deviation. 2.0 is the mean for no caffeine with 2.62 is the standard deviation here.
Okay. Wait, could you say one more time why you use sigma x instead of SX?
Well, or
the opposite, other way around, I mean.
Okay, actually, we didn't ever really talk about this. So the difference is when you have your standard deviation calculation, and I don't remember it exactly, I believe it is your x sub I minus x bar squared divided by, so it's the sum of all those divided by n. Now, if you just divide by n, and then you take the square root, I think that's the correct equation. It's actually on our formula sheet. So yeah, if you just do that, that is your population standard deviation. Now, there's a correction that's made. I can't remember, it has a name. There's a correction that's made because in truth, when you're dealing with samples, the spread is actually wider than the population. And it's not something we need to get into in great detail, but basically we make a correction, which is to do n minus 1 as our denominator. And so at this point, it's going to be S when you divide by n minus 1. So that is the main difference between those two. And you'll notice that your sigma sub x is always narrower than it's always a smaller number than the S sub x. So that just, what that does, if you think about it, it changes your distribution. If this is your distribution with the population number, then using the sample, it's going to look more like this. I mean, this is extreme, but notice how we spread the data out a little wider because there's more uncertainty when dealing with a sample. Does that make sense?
Yeah.
Okay. So there we go. We have those numbers. You might want to have them written down. We'll want to refer back to them. In fact, I'm going to write them down real quick. All right, 3.2, 2.7, 2.0, and 2.62. Okay, let's move forward. We want to find the difference of the means, which will be our x bar sub 1 minus x bar sub 2. And this we already wrote down. We decided our x bar sub 1 is 3.2. Now that's just those numbers. We didn't even really need to calculate them. And then minus 2.0. And you get 1.2 as a difference. Okay, no big deal. And I'm still going to write that down on a separate sheet of paper. X bar sub 1 minus x bar sub 2 equals 1.2. Now maybe we should interpret this right now before we move any further. What does this number mean that we just found? Okay, and back in context, it's, what does it mean?
It means that probably that there is a greater.
Okay, so on average, based on the sample alone, on average, there might be a difference of how much more beats per minute by drinking caffeine. 1.2, sure. There we go. Now, we could understand it's probably not exactly 1.2, but that's what we're going to figure out. What are the likely values based on this sample? All right. Describe the sampling distribution shape for difference of means. It's okay, that's all we're doing here. So essentially what we're getting at with this question is we want to figure out what is the spread of our data going to be? And we want to know the mean of our distribution when we have a difference of means. And then what is the standard deviation of the sampling distribution when we have a difference of means? So we know the mean is going to be right at 1.2. That's what we just calculated. But now we want to figure out the standard error. It's technically standard error in this case. But if we're thinking about it as a sampling distribution, it'd be a sigma. Maybe I can just show it as a there we go. As more of a, I don't know what I'm trying to say, using our sample data. Okay, so maybe the takeaway, the important thing to remember is that this is a combination of the standard errors of each of them, and this goes back to where we combine variances. So luckily we've already done this when we did the we've already done this main idea whenever we were looking at a difference of proportions, but the variance of a sampling distribution of standard, gosh, I cannot put all this together. Sampling distribution of sample means. Sorry about this. So let me just, I'm just going to write it down. I'm not going to try and say the words. I can't do both at the same time. So this should ring a bell at the very least. All right. And then our standard deviation of a sampling distribution of sample means, gosh, that's a pain to say, is going to be this. We want to combine the variances. Okay. And the variance is just this squared. So I need to square that. All right. So this, hopefully we're all together on this. This is making sense. So let me just show you real quick what this is going to look like. When we have our standard deviation of a sampling distribution of a difference of sample means, it's going to be square root, because we have to square root it at the end to get back to standard deviation. But we're going to end up with S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. And why does this look different right here? It's because we squared it. This is the variance. Notice that the squared was kind of distributed to the numerator and the denominator. So we squared both of them. When we square the square root, we get the whole number. When we get the original value, I should say. When we square the sample standard deviation, we get the sample standard deviation squared. Okay, so every time I talk about this stuff, I feel like I'm saying sample and distribution and sample means and sample proportions just so many times over and over that I almost wonder if they still even mean anything when I'm done talking. So are there questions on what this right here represents? And before we move ahead, I do want to show you, as you might expect, this formula shows up right here in your formula sheet. And it's under means, 2 samples. There's the sampling distribution, standard deviation. Of course, we're really using this one over here, which is the standard error. All right, so it's just a slight difference in notation, and that's what we're looking at. So of course, we would be looking at, I should just change this value right here to an S. Okay. So we're going to create another distribution shape. Let me clear all this, because that was all building up to the fact that we need to use that particular formula for our standard error. Okay, and you can see it written right there. You can see our conditions that need to be met. First of all, random, that one's kind of a given. We don't include it here. The 10% condition, that needs to be true for both samples. And the normal condition needs to either meet this central limit theorem or the population distribution has to be approximately normal. I will say, I apologize that I waited so long to grade some of your tests. I'm getting through with grading those, and I've noticed that when we were looking at confidence intervals for proportions, some people were using central limit theorem for that. We only use central limit theorem for means, not for proportions. Okay, remember for proportions, we have the large counts condition. So let's check these conditions. Let's check both of them. All right, so I've got mean 1 and mean 2 that I'm checking. And first of all, is it random? We lost our, what's it called? We lost our prompt up at the top. Do you guys remember if they said it was random? Here, let me go back a few. Here it is, sorry. So read through that, see if it says that this is a random selection.
It's not.
Yeah, it says the 20 students in the class volunteered. The assignment here was random. And random assignment, so I would just say something to this effect. The treatments in this were randomly assigned. So, and that can generally be considered okay because, I mean, think about that in terms of your science, the actual experiments used in the real world. Of course, you're going to recruit volunteers, but if you randomly assign what treatment they get, it can still be valid results. So I'll just put random assignment. Okay, and that's good for both. All right. 10%. What's our population of interest here? Well, that's our sample. What's the population that we're drawing inferences on? Caffeine drinkers versus non-caffeine drinkers. Maybe we had to add a little bit of caveat to say it's caffeine drinkers who are high schoolers versus non. But notice right here, subjects like these who drink caffeine versus. So bottom line, when it comes down to 10%, are there more than 100 people like these high schoolers who drink caffeine versus those who don't? Yeah, okay. Again, this warrants a little description, a little bit of writing. So I encourage you to do that. There are some people on these tests I'm going through and grading did not show any of their conditions being checked. That's very important to show that you're checking your conditions. You will lose points if you don't do that. And the last one, is it normal? So first of all, did we meet the central limit theorem? No, we did not. You'd have to have a sample size of 30. So is it fair to assume that the population we're drawing from is approximately normal?
No.
All right.
So we're done.
Well, all right. That's it. That's class. Have a good one. Now, we're talking about the difference in pulse rate is our variable. And where do you think this, do you think we're going to get like an extreme value one way or the other? Or do you think it's all going to fall pretty close to some kind of an average?
I think the extremes, you never know what parts of them.
That is true. I guess it, all right. Maybe I would throw in my opinion here. I feel like this will be approximately normal. And I feel like we're going to get a difference just one way or the other around the mean. And you're going to have some that are a little lower, some a little higher, very few that go out to extremes, and it'll fit into a normal model. That's my assumption. I would write that out, that I assume that the population is approximately normal. If you don't, then here's what you can say. You could say, I'm not sure that this population is approximately normal, so just understand that my results might not be accurate. All right. As long as you're expressing that you know you have statistical knowledge about why you're checking for normality, then that's good enough. Okay. Are there questions on that part? All right. Then let's jump to this. Here are your conditions again. Now, I will tell you this one right here when it says you can also check normality with a third one. That says if your sample data is approximately normal with no outliers, then you can use that as justification. But in practice, you shouldn't ever need to use that one. So basically just go to these first two, and that should be sufficient. So now we want to go ahead and construct the 95% confidence interval for the true difference in mean change for pulse rate in the two groups of subjects. All right. So remember, for confidence intervals in general, it's going to be the stat plus or minus your critical value times your standard error. And again, that is on your formula sheet. I know I say that a lot, but it's good to hear it again. Our stat in this case is x bar sub 1 minus x bar sub 2. So we saw this with our proportions. It's weird to think of a stat as being an expression. We think of it as just one number, but in this case, it's actually two numbers. So that's going to be plus or minus. It's a critical value. What kind of critical value do you think we're using here? You remember our critical values? Not the actual numbers, I want to clarify.
T star?
There it is, T star. So we either using T star or Z star. Because it's means, it's T star. Now this is where we can multiply by the standard error. And this is what we kind of derived not too long ago. The sample standard deviation of 1 squared divided by the sample size of 1 plus S sub 2 squared over N sub 2. We have our generic formula right here. We have a specific formula for this scenario right here. Now we can plug in some numbers, and we already know the difference here is 1.2. We calculated that. So now let's skip the T star for now, because you might already be having questions about that. But S sub 1, luckily we wrote that down. And you can just fill this in on your own paper. And as long as you know where those numbers come from and why we're using them, you're in good shape. So now it gets to the T star. And we need to figure out the degrees of freedom. All right. And what do you think we need to do to find the degrees of freedom for this scenario?
Do we subtract 1 from the total sample of people? So 20 minus 1.
That's a good thought. All right. There are different ways you can find your degrees of freedom, and this is where it gets more complicated. So let's just keep it simple. And this is something that's acceptable for AP. So we're going to keep it as simple as possible. For this and for our hypothesis testing later, we're going to treat degrees of freedom as your smaller sample size minus 1. Now, if they're the same size, just in this case they are, so just it doesn't matter which one you pick. So 10 minus 1 equals 9. In reality, and I want to make sure this is clear. In reality, the true degrees of freedom for this is going to be something really weird. And there's a formula you can use that will give you the exact degrees of freedom for this. But it is a complicated formula that we don't need to know. And I'm trying to think of the name of it because it's someone's last name. It's something's formula, but it's not coming to me right now. But anyways, there we go. Keep in mind what a degree of freedom is for. The higher your degree of freedom, the more your distribution resembles a normal one. If it's a low degree of freedom, it's going to be stretched out more like that. So this is low degree of freedom right here. This is high degree of freedom. So if we want to be more conservative in our confidence interval, going with the lowest reasonable degree of freedom is the best bet. Okay, because that's going to give us a wider confidence interval. So maybe our confidence interval goes from here to here rather than from here to here. And we want to make sure we're really getting 95% confidence with this. So is that making sense?
Yeah, we can just do that on the AP test, right?
Yeah.
Take the smaller one. Okay.
Yeah, just write out, I'm using the smaller n minus 1. And at worst, what you're going to do is you're going to end up with a wider confidence interval than maybe it should actually be, but that's not a problem. So anyways, degree of freedom, we want a 95% critical value for 9 degrees of freedom. So if I go, I'm looking at table B now, 95%, 9 degrees of freedom. What is that number? All right, just as a reminder. So if there's your 95%, I'm going to go up that column until you get to 9, which is about right there, if I'm seeing it right.
I got 2.262.
That is what I saw as well. 2.262. And just to repeat myself even more, keep in mind that this test is designed where you can theoretically take it without having a calculator. This is a calculation you could do by hand. It would not be fun to do, but you could do this calculation by hand and look at your T table or your table B in order to figure it out. All right, but enough of that. Let's go ahead and you can figure out at this point your confidence interval because you have all the numbers plugged in. You should be able to figure out what this interval is. I'll clear some space for you guys to write it in when you've got an answer. All right, so there you go, negative 1.49 to 3.89. That's what I got. We can interpret this in just a second. Well, let's interpret it now, and then I wanted to mention something else. Okay, so What does this mean to you when you see this confidence interval going from negative 1.49 to 3.891?
We can't conclude that caffeine makes us have a higher change in pulse.
That seems like a fair assumption to me. That would be a fair conclusion. All right. Keep in mind that if this is your confidence interval right here, notice that 0 is going to fall somewhere in that range. So with 95% confidence, we could have no difference between drinking caffeine and not drinking caffeine. We could have where not drinking caffeine actually raises your pulse rate more. So there are different outcomes. And yes, more of them result in caffeine raising your pulse rate, but there's enough uncertainty as far as that being absolutely true that we cannot conclude it. Now, I wanted to point something out because you do have in your calculator, like I've mentioned before, there are ways of doing this calculation. And I went ahead and just calculated for fun what the confidence interval would be according to the calculator. And here's what I want to point out. I'm not going to go through all the steps of how you plug this in, but if you can see this, one thing I want to point out is the very, very top. Notice that the very top, just underneath where it says 2 sample t interval, it goes from negative 1.3 to 3.6997. So that's not too far from what we came up with. So that's pretty good. That's reassuring. But then that's also far enough apart where you're like, why is theirs so different? Notice the degrees of freedom they used. 17, almost 18, but they have a weird decimal for their degrees of freedom. That's because they're using this particular formula that I mentioned, and I still can't remember the name of it. But they're using this particular formula that calculates the degrees of freedom precisely. And we just used 9. So notice their confidence interval, because they used a higher degree of freedom, it's going to be drawn in more. So it doesn't spread out quite as much as ours did. So I just want to point that out, because if you're checking your work on the calculator based on what we did, then you're going to get a different answer with the calculator. That doesn't mean you did it wrong. Ours was just more conservative. Our confidence interval spread out wider. Okay, so I think it was worth seeing that. And there we go. This is kind of the generic, well, not the generic, these are the specific formulas. We already saw this when we were looking at proportions, and now we're looking at it here in context of means. All right. And we already kind of answered this. Do we have convincing evidence that there's a difference in the pulse rates of people who drink caffeine versus those that don't? And just to verbalize this answer, we would say, like you already said, no, we don't have convincing evidence because our confidence interval contains 0, which means with 95% confidence, there could be no difference between those two groups. Okay, are there questions on this process we just went through? All right. And of course, this is no different than what you've seen before. If you have positive, positive, or negative and negative, that's going to be convincing evidence. But if it's a negative and a positive, then there's no convincing evidence. And I'm going to skip past, this is actually with hypothesis testing. We're not going to do that today. So I figured we could end with this right here. So what we're going to be looking at is right here where it asks to create a 90% confidence interval for the difference in mean pulse rates. It's funny that we're looking at pulse rates again, except now we're not looking at the data slightly different. So if we go to the prompt again, it says a researcher wanted to see whether there is a significant difference in resting pulse rates for men and women. The data she collected are displayed in the box plot and summarized below. So you have all the data. Notice it gives you what you need. We don't have to do the calculations in this particular problem. Now we can make an assumption based on the data that we're given, here's the sample mean. And that doesn't look really big, especially there's our sample size. And here's the standard deviation. So you can already draw some conclusions from this. But if you look at the box plots, maybe that can give you a little bit of guidance as well. Does that look like the average is going to be that different? You know, you can decide for yourself. So if we look at this, I'm actually going to pause the video real quick. So this answer given right here, that's actually what I calculated as well. If you had switched which one was your x bar sub 1 and x bar sub 2, then you should have the same numbers roughly, but flipped where it's negative 3.332 and positive 3.082. Okay, so that should be the only difference if you flipped which one you called the first and second sample. On the calculator, if you do this, remember, we go with a more conservative confidence interval that's going to be a little bit wider. And I want to show you the difference between this and doing the precise degrees of freedom, which is about 40. So that goes negative 3.025 to 3.2753. Notice, because we're going from degree of freedom here was 23, and degree of freedom here is 40.23, and that's really the only difference between these. That changes the critical value, and it changes everything a little bit. But notice there's barely any difference, okay? That's why going with the smaller sample size, -1, really doesn't throw off your answer that much. Okay, so it's worth seeing that. And I did not run through the entire process of this, but you know, if you do want to see that, certainly stick around. If you were not able to figure out how to get this confidence interval, let's work on that together. But essentially, this is it. We didn't run through the steps of checking our assumptions and checking the conditions for inference. So make sure now you can maybe look through it and you can determine for yourself if this met the conditions for inference. And I would say right here, from my own perspective, that it does. All right. It doesn't meet central limit theorem because neither one of these has a sample size 30 or greater, but it does come from a normal population. Okay, so that's it for today. Let me jump to the very end here, just to show the homework. Okay, if you look at these problems in the book, some of them are going to call for hypothesis testing. Some of them are going to call for confidence intervals. Obviously for tonight, just pick out the ones that are confidence intervals and practice with those. And we'll look at the hypothesis test tomorrow. Okay, and that's it for today. If you have any questions, if you wanted to run through that problem, stick around and we can go through it step by step. But if you feel like you're good to go, have a wonderful day and I will see you tomorrow.